So with our gas stoichiometry, we're going to be able to compare a starting amount with a finishing amount, or two of our starting amounts, or whatever. That's what stoichiometry is in general, right? Being able to compare the amounts of two substances in a chemical reaction. We did all of that work with moles, grams. Now we're going to use it a little bit more with our gas quantities, okay? So let's remember our main conversion factor for gas quantities. If we have 1 mole of a substance at STP, how many liters of that substance will we have? 22.4. Okay, I've heard a couple people say it, a couple people are close. Okay, so 22.4 liters is how much 1 mole of a substance, that's what its volume will be when it's at STP. Okay, when it's not at STP, we don't have that same rule. Okay, it only counts when we have 1 mole of the substance at STP. So we're going to use that as a conversion factor in our T-charts for these stoichiometry problems. Okay, we're going to do some pretty quick, simple stoichiometry problems together, and then we'll do some with a partner here. Okay, so we're going to find out how many grams of aluminum oxide are formed when we start with 15 liters of oxygen at STP. And here's our balanced chemical reaction. So go ahead and get that copied down. We'll start our T-chart here in a second. Let's go ahead and start looking at what we're going to need to solve for here. We're starting with 15 liters of O2. All right, 15 liters of O2, so I'm going to just kind of label that up here so I know what I have. And I'm trying to find out how many grams of aluminum oxide. So we're going to look at here, and we're going to try and find the number of grams. Okay. When we start these stoichiometry problems, what's the first thing we put into our T-chart? You write what you know, okay? Always write what you know. So I'm starting out here with 15 liters of O2. And I'm going to work my T-chart to end up with grams of aluminum oxide. Okay, so I'm going to work my process there to try and get to grams of aluminum oxide. So I wrote what I know. How do I get rid of liters of oxygen? Yeah, exactly. 22.4 liters is equal to 1 mole of oxygen. Okay, does this portion of our T-chart, or this conversion factor, work for every single element and every single compound? Yes, it does. Okay, it makes no difference if it's O2, H2, H2O, CO2. It doesn't matter what type of gas we're looking at. It works for every single compound. All right, so now we're in moles of oxygen. How do we go from moles of oxygen to moles of aluminum oxide? Yeah, this is our mole ratio step. Okay, so moles of O2 and moles of Al2O3. These numbers right here come from the coefficients in our balanced chemical formula. Okay, so we should have what number should go here with our oxygen? 3. Good, 3 moles of O2 to 2 moles of Al2O3. Okay, so now we're left with moles of aluminum oxide because we've canceled moles of oxygen. We've canceled liters of oxygen. How do we go from moles of aluminum oxide to grams of aluminum oxide? Molar mass. So I'm going to say mole of Al2O3, grams of Al2O3. This step in our T-chart, what does the mole always get?
1.
The 1. Okay, when we're going moles to grams or moles to molecules, the moles always gets the 1. So let's say our molar mass of aluminum oxide is? What'd you say? Okay, 101.96, we'll just round to 102. 101.96, which is about 102 grams of aluminum oxide. Okay, so now I've finished up with all my T-charts. Everything's canceled, and I'm ending up with grams of aluminum oxide, which is what I want. So let's go ahead and multiply across the whole top, divide by the whole bottom. All right, Ryan, what do you think? Do we agree? Yep, that's exactly what I got. This only works, okay, this T-chart only works when we are at what conditions? STP. Okay, this conversion factor, this T-chart only works when we're at STP. Okay, if we're not at STP, we're going to have to do some other things to get through that. Okay? Very good. Now we're going to look at how many liters of water we can make from 6 grams of H2 at STP. So this time we're starting with grams, we're going to end up with liters. Okay, so this is basically just working backwards from what we just did. Do we need to do this as a class, or are you good to go on your own? Okay. What do we get for our liters of H2O? 67.2 liters H2O. Okay? I agree. Okay, a phase in chemistry terms is any part of a system that has uniform composition and uniform properties. Okay, it's very similar to a state of matter, okay, as being in a phase. So if you're in the liquid phase right now, you have all liquid particles. Okay, all of those liquid particles look the same, they act the same, they have the same composition and same properties. Okay, when we say they have the same composition, it means they're made up of all the same elements and all the same arrangements. Okay, so exactly the same molecules. So I want you to go ahead and take a look at page 342. I want you to copy this table 2 down into your notes. Okay, this has to do with phase changes and their names. We talked about these just a little bit when we started our vocab for this chapter 10 section, but I want you to kind of get this table in there, and then we'll start breaking each of these phase changes down a little bit more in depth. All right, so if you don't have the table all the way done, that's okay. Keep working on it as we go through. We're going to break down each of these phase changes just kind of in brief so you get a little bit better idea maybe of what they are and what goes into them. We're not going to go very extensively into them, but we are going to talk about them just a little bit. So when we talk about condensation, where the most often do we see condensation taking place? Yeah, like on glass surfaces is mostly when we see it, right? If a glass is sweating, we call it sweating in a car, things like that. That forms condensation. Okay, when we're talking about condensation, we talk about a gas that's changing into a liquid. Okay, so it's vapor. A vapor is basically liquid particles that are consuming enough energy to become in a gaseous state. Okay, so it's not a true gas. It's still kind of liquid particles that are broken up into a gaseous kind of state. Okay, so when we turn that vapor back into a liquid, is it cooling down or heating up when something condensates? Yeah, it's cooling down, right? It's losing energy because it's coming from a gas to a liquid. Okay, gaseous particles typically take more energy to remain at that gaseous state or vaporous state, and it takes less energy to be at a liquid state. Okay, so when something's cooling down, what we're doing is removing energy. Okay, we're removing energy in the form of heat. Okay, so when something condensates, it's losing energy, it's cooling down. Okay. We're going to talk about something called equilibrium. Okay, equilibrium in and of itself is basically when some system reaches some sort of a balance. Okay, when something is at balance. So we're looking at something called vapor pressure equilibrium. So this is when two opposing changes occur at equal rates. So when a liquid is going to a gas and a gas is going to a liquid at the same rate. Okay, that's what equilibrium kind of means. So if you turn to page 343, it gives us a good example of what equilibrium looks like for vapor and liquid systems. Okay, so if you look at figure 13, part A of that picture, it says, at first there are only liquid present, but molecules are beginning to evaporate. Okay, so we reach equilibrium in what we call a closed system, and which means nothing can kind of escape or come in. Okay, so closed systems can be anywhere from as small as this little flask. It could be this room. It could be any sort of closed system that you think things are contained. Okay? So in part A, it says there's only liquid particles present. So those green molecules in here are substance, whatever substance this is. When they're kind of at rest, that means they're a liquid. Okay? In part B, it says evaporation continues at a constant rate. What's it mean when something evaporates?
Loses energy. Becomes a gas.
Yeah, it becomes a gas, but it gains energy, right? It gains some sort of heat energy. So evaporation is going from a liquid to a gas. Okay, so there's some sort of heat source on this flask or this system that's causing those things to evaporate. Okay, because in order for something to evaporate, you've got to have some sort of energy that's being added to the system. Does that make sense? Yeah, the sun can evaporate certain things. In this flask, if it was being heated from below, that's why those things are rising, right? Because it's being heated up and they'll start to rise. Okay, in part C, it says equilibrium has been reached and the rate of condensation equals the rate of evaporation. So what this is saying is that these liquid molecules start to evaporate. They start to raise up in this container. Okay, they start to become gas molecules in which they bounce around in this within the walls of this container. Are we on the same page so far? Okay, as those molecules start to get farther and farther up or away from that heat source, they're going to start to cool down. Right? As they move farther and farther away from that heat source, they're going to start losing energy and starting to cool down. If they cool down enough, they'll condensate back to a liquid form in which they drop back to the bottom of the container. Okay? From there, they'll start to heat up again and start to evaporate again. That's what we mean when we say equilibrium, is that one of these is evaporating and one of them is condensating all at the same rate. Okay? So basically when one evaporates, one has to be condensating as well. Does that kind of make sense? So they got to be happening at the same rate. Okay? We can't be all evaporating and no condensation, because then there wouldn't be an equilibrium. Okay? Yeah.
Is that why, like, if you boil water in a pot, that goes good?
Mm-hmm. So when we say we have vapor pressure, that means those particles that have become gas or become a vapor are starting to kind of hit against the walls of these containers or collide with the walls of these containers and starting to cause a pressure. Okay? When we get enough gas particles that are moving around in a container, we're going to start to have pressure. You ever notice when you leave a pop in your car when it's hot outside and you open it and it either explodes or it makes that really big sound or it's becoming stiff, right? The walls of the container are stiff. Have you ever noticed that? When a pop gets hot, it becomes stiff. That's because those molecules are beginning to evaporate, which means those gas particles are bouncing off against the walls of that container, which are making the container stiff. Okay? So once it reaches that, probably that pop has started to reach equilibrium vapor pressure. If not, it's starting to become too much vapor pressure and it's going to explode if it heats up too much more. Okay, so you don't want to leave your pop in your car if you don't want it to explode. Okay, on a really, really hot day. It'll take a while for it to get there, but it might. Okay, so equilibrium vapor pressure just means it's pressure that it's exerted by that vapor in a closed system. Okay, so when those gas or those vapor particles start moving, start vibrating, start bouncing off the walls of that container at a fast enough rate, we're going to cause some major pressure within that closed system, within that container. We see pretty high levels of vapor pressure in what we call volatile liquids. Okay? Can anyone think of anything that might be considered a volatile liquid? Something that evaporates really quickly.
Gas.
Gasoline is one. CO2, yeah, we don't see it in liquid form very often, but that's because it's pretty volatile. Let's think. Girls, when you take fingernail polish off, do you know what that's called? Acetone. Acetone is really, really a volatile liquid. Anything that you can pour out and it starts to evaporate quickly is what we consider a volatile liquid. So if I spill acetone on the tabletop, it won't last more than 5 or 10 seconds, depending on how much I spill. It'll just start evaporating and it'll be gone. Okay, it evaporates that quickly. Gasoline is pretty close to that, but not quite as quick. But those are considered volatile liquids. They have really, really weak intermolecular forces, which means that liquid can become a gas with very little energy added. Okay. Boiling just a little bit. Boiling is converting a liquid to a vapor, okay, or to a gas. So within the liquid as well as at its surface. So when you boil something, you notice the bubbles don't start on top of the liquid, right? They start underneath. They start within the liquid. Have you ever watched a pot boil? Okay, or a pot of water boil? Those bubbles start at the bottom and they start coming to the top. Okay, so boiling something means we have an addition of energy. We're adding in energy because we want those liquid particles to become gas particles. That's not necessarily why we boil water, but it's a part of what happens when we do, right? When we talk about something called the boiling point, that's a certain temperature for every substance has a specific boiling point. Okay, so water has a different boiling point than carbon dioxide, than hydrogen, than whatever. Okay, every single compound has a specific boiling point. Okay, and that boiling point is reached when we have an equilibrium vapor pressure that's equal to our atmospheric pressure. Okay, so that pot or that water, whatever that's boiling, will reach an equilibrium state. Okay, it will keep boiling at that constant temperature as long as pressure stays the same. Okay, so as long as pressure remains constant throughout this entire thing, we're going to be able to have a constant temperature. Okay, at the boiling point, which we abbreviate BP. But our boiling point increases as we increase the strength of our intermolecular forces. Okay, the stronger the intermolecular forces, that means the more energy that's going to be needed to break those, right? You're going to have to add more energy to break those intermolecular forces. So the stronger the intermolecular forces, the higher the boiling point. Okay? So which things on the periodic table, which compounds on the periodic table typically have the weakest intermolecular forces? The left side or the right side? Which have typically weak intermolecular forces? The right side, right? The covalent bonds typically have pretty weak intermolecular forces. You notice most of these on the right side are the gases, right? Gases are on the right. They have weak intermolecular forces because gas particles are constantly moving. They're not holding together very well, okay? So those have weak intermolecular forces, which is why they're mostly all gases. Does that make sense? So they have very, very low boiling points. Things down on the left side of the periodic table, specifically the metals, things on that side, are going to have pretty strong or pretty high boiling points. Strong intermolecular forces equals high boiling points. Okay, it takes a lot of energy to break that down. Okay, so when we freeze something, we're taking it from a liquid to a solid form. Does that mean a removing energy or adding energy? Removing, right? We're cooling it down, so we're removing energy. Very good. Okay, it's a loss of heat energy. We're going to get through these last ones kind of quick here. So freezing is going from a liquid to a solid. And then we have something called sublimation, which means we're going from a solid to a gas. Okay, and there's one really common example we can think of for sublimation. Anyone know what it is? Yeah, dry ice is really the only kind of real-world example for sublimation. We don't even use dry ice that often. Okay, that's not that common of a thing, but that's our most visualized kind of example of sublimation. Okay, so that's going directly from a solid to a gas. The opposite of sublimation is what we call deposition. Deposition is when we go from a gas straight to a solid. Okay, can you guys think of any examples for that? For sublimation, going from a gas to a solid. This one's a little trickier, okay? And one example that I can give is when you have frost on your windshield in the mornings. Okay, everyone understand? We have that issue before, right? You come out in the morning and there's frost all over your windshield. You don't see individual water droplets that are frozen to your windshield, right? You see kind of a nice, like, crystal-like layer. That's kind of an example of sublimation. That water vapor freezes before, and it doesn't really take much time to stop at the liquid phase. Okay, so all that water vapor that's in the air will just freeze after it reaches a certain temperature. It doesn't really take time to solid or condense to that liquid form before it freezes. That's why you don't see a bunch of water droplets frozen to your car. You see kind of a nice layer of frost. So they become more kind of like crystal, like frost structures. Okay, does that make sense? Okay. So now we're going to talk about our last section for today. It's called a phase diagram. All right, a phase diagram is a graph, and it shows us pressure versus temperature of certain substances, okay? So a phase diagram tells us what state of matter or what phase a certain substance will be in at a certain temperature and a certain pressure. So we're going to follow these graphs to find out if we're at 300 degrees Kelvin, or we're at 300 Kelvin, and we're at 16 atmospheres, is our substance going to be a gas, a liquid, or a solid? That's what phase diagrams tell us. Okay. Phase diagrams are substance specific. Okay, and what that means, these are substance specific. What that means is that each individual substance has its own phase diagram. Okay, and that will make a little bit more sense after we look at them in a little bit more in depth, but each and every substance has its own phase diagram. The one we're going to look at is for water. So we're going to take a look at this phase diagram that's in front of you here. Thank you. What we're going to do first, your first goal here, and I'm going to give you only about a minute to do it because we don't have much time, is that you're going to color these or shade these in with your colored pencil, each of the three phases. So the solid phase, which is all of this section from this dark line to this dark line where it's labeled solid, that's going to be one color. This liquid triangle is going to be another color, and then this gas phase under here is going to be another color. Okay, so that you need to do that within about a minute, minute and a half. We're kind of on a time crunch here. The label on your diagram is called the triple point, okay, and that's point D on your diagram. Point D on your diagram is what we call the triple point, and this is what it means. It means that at this point, at this temperature and at this pressure, right, D is a point between 0.006 atmospheres and 273.2 Kelvin. So you need to copy these temperatures down on your table as well. Okay, these temperatures down here that correspond with the dotted lines. If we have water that's at 273.2 Kelvin and 0.006 atmospheres of pressure, it can be a solid, a liquid, and a gas all at one time. Okay, it can be all three of those states of matter. They can all be at equilibrium. Okay, that's what the triple point means. So at 273.2 Kelvin and 0.006 atmospheres of pressure, all of those three can be at equilibrium at one time. That's what we call the triple point. Okay? And these temperatures and these pressures only work for water. Okay? These are substance specific. So carbon dioxide would have a different phase diagram with different numbers that go into it. Okay? This one right here is 273.2 and 0.006. So you see where those two dotted lines come together and meet at point D? You need to have this one too. The first dotted line that goes up to this point is 273 Kelvin. So you need to have that down on the bottom of your table. This one's 373 and this one's 647. Okay?
Is there like an example of that?
What do you mean? All right. Our next point we're going to talk about is point E on your table or on your graph, which is called the critical point. So on these 2 points, you might want to label those triple point and critical point. Critical point's up here at the top, okay, and it's point E on your graph or your diagram. What this means is at point E, once we reach a temperature of 647 Kelvin and 218 atmospheres of pressure, even the gaseous state of water can no longer exist. Okay, it gets to be too much temperature and too much pressure. It doesn't work anymore. Okay, so things start breaking down altogether. And here's our temperatures for that. So 647 Kelvin or 370, basically 374 Celsius and 217.75 atmospheres, or 218, which is what's listed on your table, which is fine. Okay, so those are our values for the critical point. All that these values are telling you right here are the same things that your diagram is telling you. So 647 Kelvin and 218 atmospheres, which is what those are telling you. Yeah. Okay. All right, so now let's look at these curves on the graph. You see this curve on yours labeled curve C, which is right here. This is curve B right here. And this is curve A. Okay, so let's just talk about what these mean. These are called equilibrium curves. Okay, so along these curves, these two phases can reach equilibrium. Okay, so let's look at curve A first, which starts from the base and goes up to the triple point. Okay, starts from the base and goes up to the triple point. It's right here. Which two phases are on both sides of this curve A? Solid and gas, right? Those are the two phases that you have on either side of curve A. So what this is saying is that along that curve, if you reach an intersection along that curve, maybe you have pressure about here and temperature about here. If you reach a spot on that curve, that means that vapor or gas and solid can be at equilibrium at that point. Okay, so solids and gases can be reached at equilibrium if you're somewhere along this curve. What if I have a temperature of, let's say, 200 and a pressure of 0.006 atmospheres? What state of matter or what phase would I be in then? Solid, right? Because I went 200 degrees and I went all the way up to 0.006 atmospheres, which means that my graph tells me, or my diagram tells me, that I'm in the solid phase. So that's how we read this diagram. Does that make sense? Okay, so if I reach somewhere specifically along this point, then I'm at equilibrium. Okay, if I'm on that line directly. Curve B, which two phases would be at equilibrium at curve B? Solid and liquid. Okay, solid and liquid. So curve B is the temperature and pressure conditions at which the solid and the liquid phases would be at equilibrium. Okay. And then can we take a wild guess at curve C? Gas and liquid. Okay, so if we look at curve C, that means our gas and our liquid phases would be at equilibrium.